Hello, this is Grzegorz Łabus from the Rotterdam Ophthalmic Institute and the University of Murcia. And I'm also an early-stage researcher to the HI Mercury ITN project. In this video, I'm going to tell you about stellar evaluation of intraocular lenses. But at the beginning, I want to give you some background information to show why this is such an important subject. So let's start with some terminology. This is a normal eye with the natural lens, and this eye is called phakic eye. When cataract develops and the crystalline lens turns opaque, it is removed and replaced with an artificial intraocular lens. And then the eye with the intraocular lens is called pseudophakic eye. Although cataract surgery removes the main source of stellar increase in a cataractous eye, the lens, it's not always the case that stellar comes back to the level of a young eye after surgery. And as you can see in this figure where stellar of the pseudophakic eye versus age is presented, only 8% of pseudophakic patients show stellar levels of the young eye following surgery. It's true that on average stellar decreases after surgery, but when you look at data points of individual patients and when we compare preoperative stellar and its improvement after surgery, then it becomes clear that some patients experience stellar increase after surgery, and this affects 18% of pseudophakic patients. Further analysis of this large population data shows that 10% of pseudophakic patients suffer from a condition called serious stellar hindrance, a stellar value of 1.50 log S. Just to give you a sense what the functional effect this condition may have, please take a look at these figures. Here is a simulation of normal vision with a normal stellar level, and this may happen when stellar goes up to 1.50 log S. Keep in mind that this condition is not only related to difficulties while driving at night or against a low sun, but also hazy vision, decreased color sensitivity, and problems with face recognition. And one may wonder whether general stellar elevation in pseudophakia is related to implanted intraocular lenses. Studies have shown that scattering of new IOLs is low, but the question is, how does it change after implantation? To address this question, we measured stellar of 6 explanted intraocular lenses that were removed from the eye for other than stellar reasons, such as subluxation or postoperative refractive error. For stellar measurements, we used this device, that is the sequence stellarimeter. This instrument was designed to assess in vivo stellar of the eye. It works based on the compensation comparison method that was described in details by Luke Francis in this paper. Just very briefly speaking, a subject fixates on the test field that is divided into two halves. During the sequence procedure, the stellar source, this ring, starts flickering in black and white. Then, because of stellar of the eye, part of the light is projected onto the fovea. A weak flicker appears in the test field, which with zero stellar would appear black. Because in one half of the test field the compensation light is added, essentially this measurement is a comparison between known and unknown intensity levels. And this approach could also be applied to assess stellar of IOLs, but for this, the sequence needs to be adapted. The sequence adaptation was designed using optical software, and this consists of two converging lenses, here and here, a wet cell to keep the intraocular lens in solution, and an iris. The most important part of this adaptation is the iris, as it blocks rays of the scattering ring. So the observer's eye is not exposed to the stellar source, while the test field can still be seen by the observer who performs the test. And this precisely allows us to measure stellar of the intraocular lens objectively, without interference of stellar from the observer's eye. And here is a ready-to-use sequence adaptation for stellar assessment of intraocular lenses. This is the first lens, the cuvette, the iris, and the magnifying lens. Because we assume that there might be some light scattering taking place in the adaptation, stellar of the IOL is calculated as a linear subtraction of stellar of the setup with and without the intraocular lens in place. To validate the sequence adaptation, we use two commercial scattering filters measured separately and stacked together to obtain 3 scattering values. And as these values are known, we could calculate expected stellar using this formula, and we compared it to measured stellar levels. Here are the results of the validation procedure. But before I start to discuss them, I want to explain this quite complicated looking graph. As you remember, we used two scattering filters and their combination. We also assigned three observers with different strata of their own eyes to perform validation of the setup. The observers measured two monofocal and one multifocal IOL, and the test was also done without any intraocular lens in place. As you can see, a very good absolute correspondence and high correlation was found between the measured and expected stray line. This proves that the sequence adaptation and the procedure give proper absolute values and can be considered as an objective measure for stray line assessment in intraocular lenses. The mean stray line parameter of the studied IOLs was 5. The individual stray line parameters range from virtually 0 to over 12 units. 3 out of the 6 analyzed lenses show stray line below the level of that of a 20-year-old crystalline lens. 2 explanted intraocular lenses showed increased stray line that reached the level of that of a 70-year-old crystalline lens. In conclusion, a new method for assessing stray line of intraocular lenses was proposed and validated. Some of the routinely explanted intraocular lenses showed increased stray line up to a level known to be of functional significance, and this points to the IOL as a potential reason for stray line elevation in pseudophakia. The sequence adaptation is not only limited to IOLs, but this can also be used to study scattering properties of any type of material, such as contact and ophthalmic lenses, scattering filters, or biological tissues. And this new methodology delivers a functional stray line parameter, which allows a direct comparison between in vitro and in vivo values. Thank you for watching this video. I hope you enjoy it.